This video we'll be looking at the schema view of the sequencer that I just showed prototyped on a breadboard. Our goal here is to investigate this layout, learn a little bit about using a schema, which is the KiCad tool for laying out schematics. And ultimately, in the next video, we'll be taking this schematic and turning it into a PCB design which can be sent for manufacture. Here is the sequencer essentially as built on the breadboard. First, I'm going to talk about the structure of this page. It's got some grids around the edges in the bottom corner. It's got a source from which I developed the idea for this circuit, and the name, and then the file, which will be a .sch for the schematic. This entire project is in a folder that's also called sequencer. Sequencer.pro is the project file, and there will eventually be some other files generated as well. In particular, sequencer.pcb will be generated for the actual PCB layout. Again, that'll be in the next video. I'm using KiCad 5.1.9 on Mac OS. So the cursor, again in KiCad, zooms to wherever it's centered. It's pretty convenient. So I zoom out here, we can see the entire schematic. Notice there's some parts to it. There's one part up here which handles the power that comes in on the same sort of connector as the VCO. There are some flags here which explain what the different power symbols are and where they're connected. And the way this works is that on the power connector, as usual, plus and minus 12 and ground. We have some capacitors for filtering, and then these symbols which indicate this is a plus 15 volt and minus 15 volt and ground source, and then these flags are identified to be used throughout the rest of the diagram. Now, unlike the VCO, the sequencer is not going to require any of the negative voltages. That is, this particular circuit does not have a bipolar power supply, but the power port is brought into the board anyway. Anytime that then I use either a ground symbol or the arrow with the plus 15 volt symbol, both of which are obtained from the power supply button, which is the usually has the ground symbol representing it over on the right hand toolbar. I can bring 15 volts or ground anywhere I want in the circuit. For instance, over here where the voltage comes in that powers the 4017 decade counter, that is simply labeled, and it's understood that it connects through these power supplies. I don't have to actually draw a wire to them. This makes the diagram a lot easier to look at. You can continue with this idea and break up schematics into multiple pieces where you have labels not just for power but for different signals as well. So we talked just a little bit about the functioning of the sequencer, which is a variant of the original Baby 10 sequencer published by Captain Analog many decades ago. This particular design is closely related to the implementation by Herman about 10 years ago. And the idea is to have an oscillator, which is a low-frequency oscillator that sends out a clock pulse that triggers this decade counter. The decade counter then sends out sequential signals on each of up to 10 wires, which we use in the sequencer to do several things. Each pulse is used to form a control voltage with a potentiometer. So, of course, a potentiometer is a voltage divider. We take the center pin off the potentiometer and send that to a CV out. Each potentiometer output on each individual sequence needs to be insulated from the other ones. You don't want the voltage produced, say, by channel 3 here to run back into, say, channel 2 and affect things. Therefore, a diode is added to each output. And so the net result of this CV out is exactly what we saw on the breadboard version. This was, the voltmeter was reading the voltage series that came out, and this is what we were sending in to the VCO to make different tones. So again, each of those potentiometers fires in sequence. See, each of them is attached to a different output of this decade counter. Now there's two more, actually in fact 3 more connections on each wire. One of them is simply an LED, which we used for visualization, so you could tell when it was firing that everything was working, and that's just a LED that is in series with a 2.2K resistor as a current limit. These all share a common ground, and I'm going to zoom in here at the bottom of the connection. Notice there's a dot on the lower side of each pot and a dot on the lower side of the LED resistor. That implies that there is a connection there. The third wire connected to each output, which is in the middle of my grouping, does not have a dot. So there's no connection here. So this is just a place where the wires cross, and via the standard convention they're simply drawn as a cross, whereas the dots are necessary to say you have a connection. If you want to put a wire on the diagram, you use the green wire line. If you want to force there to be a dot connection, if KiCad doesn't figure it out on its own, you grab and stick one down with the node tool over here. This second line just simply has a diode coming out. So this really is the raw output of this decade counter. And the raw output goes through another diode that, again, just prevents feedback to other parts of the circuit. And they are all linked together. And all 8 of them are chained up to come out on what's called a gate out. This is a signal I did not demonstrate in the last video, but is used to produce a series of gate outputs that tell you when the tone is on and off for use in subsequent modules, such as the envelope generator like the ADSR, which we'll be building next after we're done with the sequencer. The gate out and CV out are both the most common two, along with trigger signals, used in modular analog synthesis. There is a fourth wire attached, and it's drawn as going straight through. And each of them goes to an individual connector here, which is labeled J4. So this would be like, say, imagine 4 header pins is what I have in mind for this. And each of these pins is connected to one of the outputs. And this is not a signal that will leave the board in the current implementation, although it does in some people's designs. Instead, what it does is it can be jumpered across with a small piece of wire to the J5 set of headers here. And the difference between J4 is each of these are individually connected to the outputs, whereas J5, all of them are connected together. So a jump from one across connects this output to this line, or jumping 6 across connects 6 to this line. And what this is a mechanism for doing the resets at different times. Because this wire runs up and over and into the reset of the decade counter. So just as I demonstrated in the videos, if I only wanted the first, say, 3 lights to fire in sequence rather than go through all 8, I would jumper across number 4 here, and then the moment I want lit up lights 1, 2, 3, by the time I hit light 4, it would reset and then jump back up to the first LED. And so I just have a running train of voltages that were 3 beats in sequence rather than 8. This could be done alternative ways with a rotary knob or a dial or a set of switches. In my case, this will be implemented as something you have to actually go onto the module board and change, but at least you'll be able to change it. Couple other things about the 4017. Again, it's a decade counter, and that means that it takes a clock impulse in, and every time the clock changes state, it advances the output. Its purpose is to count to 10, and for the moment, the final 2 outputs are not used. Q8 and Q9 on pins 9 and 11 are used to potentially connect to resets. They go straight through, but they do not fire LEDs or create outputs. The reason here is that typically 8 beats sound a lot better in music than 9 or 10. I'll be asking you to do a modification just on paper to add those last ones in. For that reason, I have numbered all of these potentiometers, current limiting resistors, LEDs, and the 2 resistors, 2 diodes on the output, all have been labeled with a number, grouping them together. So pot 10 is connected to Q0, R10, and D10, D20, and D30 all are connected to Q0, which would be the first output to fire. 11s, 21s, and 31s go to Q1, 12s, 22s, 32s to Q2, etc. So the 17s, 27s, and 37s would be the 8th output, and there is no pot LED or current limiting resistor labeled 18 or 19, and no output diodes labeled 28, 38, 39, or 29. Few other details. The reset, like all the inputs to these CMOS chips, always need to have a signal connected to them. There is a enable, which needs to be set permanently low to ground for the chip to run. There is a reset, which we're using on the off chance that we don't have one of these connected over in our jumper. The chip will go extremely haywire. We saw an example of that in my breadboard video. And produce random outputs and potentially start to draw a lot of current and maybe even damage itself. So it's always connected through a resistor. This is the 51K resistor that's in your kits to ground. There's an indicator LED that shows when the trigger is firing, and that trigger can come from one of 2 sources. It either comes from a input plug, So you can bring a trigger in from another low frequency oscillator, or perhaps the trigger out of a MIDI keyboard. We'll be building one of those with our final module in the class. The MIDI to CV will also have a trigger output that we can use here. So it could use a keyboard to then use this to create a note sequence after each press of a keyboard. Or alternatively, and sort of by default, I guess I should say, the clock input will actually come from a 555 timer operating in astable oscillation mode. So by now we're very familiar with this sort of circuit. There is a power supply that goes through a pot. That was the pot on the right-hand side. And that will affect the RC time constant of this line, which here's the capacitor, 22 microfarads electrolytic capacitor, and it's when it passes the threshold value that will cause the output, which is here labeled Q in this place. This is the output of the timer to switch. A diode prevents currents from running back in, perhaps from the external source. And there's a 10K resistor in series to make sure that when a plug is put in, that when the site is grounded, the timer continues to run just fine. So those are the main features. A couple other details. It is really important when dealing with these CMOS chips to not give them spiky signals or stuff with a lot of noise. So I have added filter capacitors to smooth out the power draw on the 555. One well-known disadvantage of the 555 is that it produces spiky outputs by suddenly surging on its power draw when it flips state. So like when the threshold flips and the output changes. The typical solution is to have one large capacitor which can hold a lot of energy and slowly charge and discharge to smooth things out, and one smaller capacitor, in this case the 10 nanofarad, which handles rapid fluctuations at early times in switching. And so this little solution you see is also used here on the power supply of the 4017 as well. So they bridge to ground. So any fast fluctuations get shorted out, allowing the DC voltage that goes through smoothly to continue. The same motif we saw in designing the main power supply. These particular capacitors should be placed as close as possible to the grounds and inputs of the device once we get to the PCB layout. Again, there's our overview. I'm going to now move a few components around and hopefully put them back in the same place. So one of the assignments I'll be giving the class is to add a 8th and 9th set of outputs. So the way to do that is, first of all, to make some more space here. And so I'm going to do that using the selection tool. So your default tool you want to be in. There's many ways to do this task. I'm just going to show you one of them here. I'm going to grab these. And see, once I grabbed it, it moved. And it's moving with me. And then I am pulling it out, right, moving it around. And wherever I click the button, it's going to set it back down. Now I could use this way, but then I'd have to redraw my wire connections if I wanted to spread it out like this. And that would be a bother. So I could just go and either try to put this thing right back in place, or alternatively, if it's too annoying to try to match it up exactly, or I'm worried about getting it exactly right, instead I can hit escape, and it says if that operation didn't happen. If I had clicked down, I would go up and use the undo function. Instead, I'm going to try to move it in a more sophisticated manner by just grabbing the stuff I want, and then without moving the cursor after selecting, I'm going to select drag block. A block is a grouping of components, anything I just selected. So drag means drag a component along with its wires. Move means move it without wires attached. Let's try the drag. And see, now I'm able to just slide it out nicely. I have to keep it straight, of course. There we go. And now I probably should do the same to these audio jacks. Right click, drag block, and now I can start copying and pasting as I'd like. Duplicate is often the easiest way to do stuff. I got a little more than I bargained for here. But I could place this down and then begin moving individual components. Let's see about editing and changing a component. So if I double click, it brings up symbol properties. I can also get to this by right clicking and going to properties. The reference is the name I call it. The value will have a meaning for a resistor or a capacitor, no particular meaning in the case of a diode. Footprint is important. We have to have a footprint before we put a PCB. We haven't chosen a footprint yet. And there may even be a link to a data sheet. The link to the data sheet is purely optional. The reference, the value, and are needed for the schema, and the footprint is needed for the PCB view. And if you go through the tutorials, you'll notice that you can rotate and flip these, not just using this menu, but also directly after right-clicking on the object. Useful thing is you can move the references around, rotate them, etc. Notice how they say tethered to the object that they're placed at. This is just for formatting purposes. All right, I'm going to undo all of my changes here. And next we'll be assigning footprints and moving towards making a PCB. Spend some time playing at this point and doing the first task, which is to add those extra couple of pots and LEDs and outputs to make a true baby 10 from this baby 8 step sequencer.